Hello friends, how are you all? This lesson is all about open system analysis. Previously we have learned the closed system, work transfer in various processes in closed system, heat transfer in various processes in closed system, different equations of closed system with the help of ideal gas equation, all that we have studied. Also we have discussed the objective questions related to closed system. Previously all the concepts was related to closed system. From now the open system will come. In this particular lesson we will discuss the steady flow energy equation, the derivation of steady flow energy equation, which is very important. Then we gonna discuss the application of steady flow energy equation like in turbine, compressor, nozzle, diffuser, throttling valve. All those applications we are going to learn in detail. But before proceeding further, I would like to introduce myself. My name is Harshit Agarwal. I have graduated from NIT Nagpur in 2008. This is all about me. You can always rate, review, recommend, and share this course. You can also follow me on the specified link. So, to start with, first of all, what is flow work? See, the open system analysis is completely based on the control volume concept, right? Consider this as a control volume. Consider this as a control volume, and you know that the work done on the system is taken as negative, and work done by the system is taken as positive. On the system हम लोग negative लेते हैं, by the system हम लोग positive लेते हैं, right? This is a control volume. This particular thing is a on the system. I mean, this is the fluid element which is entering into this control volume. Please try to understand here. This is a fluid element which is trying to entering this control volume. We have to do the analysis of this particular control volume, right? So for time being, this is the system, and this fluid element is entering into this control volume. I mean to say, this is doing work on the system. Similarly, the moment this fluid element goes out of this control volume, then some kind of work is going to be done by this fluid element. So this is work done by the system. So fluid element entering into the control system is known as entry flow work, which is negative, and the fluid element exiting by from the system is exit flow work. So, what is flow work? It is basically the work transfer. Flow work is basically the work transfer involved in causing the fluid element either to enter. This is the fluid element which is trying to enter or to leave the control volume, or to leave the control volume is known as flow work. Right, so how to calculate this entry flow work and exit flow work? To find the entry flow work, we know that W is equal to pressure into area into distance, right? So pressure into volume is what? Pressure into volume is work. Fine. So force into distance, pressure into area is force, into displacement is dx. So if we want specific volume, we will divide by mass. So minus p1 v1, minus p1 v1 is the entry flow work. Similarly, plus p2 v2 is the exit flow work. And there is one more kind of work which is the control volume work. See here, three kinds of work are there. This is the flow entry flow work one. The moment the fluid element enters this control volume, it is entry flow work minus P1 V1. The moment this fluid element leaves the control volume, is it exit flow work plus P2 V2. And the amount of time this fluid element is there inside the control volume, the amount of time this fluid element is there inside the control volume, it will do some work which is the control volume work. Right. So entry flow work is minus P1 V1, exit flow work is plus P2 V2, and control volume work is WCV. So the amount of time this fluid element is inside the control volume, it will do some work which is the control volume work. So the net work comes out to be control volume work is by the system, that is it is positive. Exit flow work plus P2 V2, it is also positive, and entry flow work minus P1 V1, it is negative. So the net work is control volume work plus entry flow work minus exit flow work. So the net work is WCV plus P2 V2 minus P1 V1. This is the net work which is being done. Just keep in mind this net work equation. Next, what is this steady flow energy equation? See, steady flow is something in which the properties do not vary with respect to time. There are two important equations related to steady flow. One is the mass conservation and second is the energy conservation. Mass conservation equation is nothing but the continuity equation, which I will be explaining in fluid mechanics. Right. So what is this steady flow energy equation? For steady flow, properties do not vary with respect to time at any given section. And hence for steady flow, mass entering, the amount of mass entering and the amount of mass leaving is same. Mass entering and leaving the control volume is same. The amount of mass entering in this control volume and the amount of mass leaving from this control volume is same. Similarly, the energy entering and leaving the control volume is also same. The energy entering this control volume and leaving the control volume is also same. That is, for steady flow, there is no accumulation of either energy or mass in the control volume. Keep this statement in your mind. This is the very, very important statement. There is no accumulation. There is no accumulation of either energy as well as mass in this control volume. That means dm by dt, mass with respect to time in control volume, is equal to 0. That is, mass entering this control volume is equal to mass leaving this control volume, which is equal to m. There is no accumulation of either mass or energy in the control volume. For steady flow, keep in mind mass entering and leaving is equal to m, which is same. Now, conservation of energy. See, this is the control volume. In point 1, there is kind of internal energy U1, there is pressure P1, there is volume V1, velocity is C1. Similarly, for exit, there is internal energy U2, pressure P2, volume V2, and velocity is C2. We know that there is no accumulation of energy in the control volume. So total energy entering, that is potential energy, kinetic energy, internal energy, and heat supplied. Heat supplied to the system is taken as positive, and the total energy leaving, that is the internal energy, pressure, potential energy, kinetic energy, and work done by the system, is energy out. So total energy in is equal to total energy out. So total energy in comprises of kinetic energy, potential energy, internal energy, and heat supplied, and the total energy leaving is kinetic energy, potential energy, internal energy, and net work. It is net work. And we have studied that. See, here is pressure term, here is pressure term. So what is the use of this pressure term? This pressure term helps you in calculating the flow work, and that flow work we have already considered in the net work. वो जो फ्लो वर्क है वो हमने नेटवर्क में ऑलरेडी कंसिडर कर लिया है, राइट. सो हम नेटवर्क पे ये वाली इक्वेशन बिल्कुल लिख सकते हैं. that this equation we can write in place of network, that is control volume work plus P2 V2 minus P1 V1. That is control volume work plus P2 V2 minus P1 V1. So kinetic energy, potential energy, internal energy plus Q is equal to kinetic energy, potential energy, internal energy. Net for network we can write minus P1 V1 plus control volume work plus P2 V2. Shift this minus P1 V1 on left hand side. It comes out to be kinetic energy, potential energy. U1 plus P1 V1 is what? Enthalpy. U1 plus, we can write U1 plus P1 V1 as enthalpy. Enthalpy is basically used in open flow. And U2 plus P2 V2, right, we can write enthalpy. So the final equation per unit mass, for the final equation per unit mass comes out to be H1 plus C1 square by 2 plus GZ1 plus small q plus H2 plus C2 square by 2 plus GZ2 plus W. Keep this equation in your mind. This is the first law of thermodynamic equation for steady flow. This is the first law of thermodynamic equation for steady flow. This is a very, very important statement. Every time in Indian Engineering Service examination, at least 2 or 3 questions are asked on this particular equation. This is a very, very important equation. Keep this equation in your mind. So, some detailed part of steady flow. This is the steady flow equation. From steady flow, we will see how the Bernoulli's equation is derived. Consider adiabatic and W0. Q and Q cancel out. U1 is equal to U2, internal energy initial is equal to final internal energy. The equation finally becomes P1 V1 plus C1 square by 2 plus GZ1 plus P2 V2 plus C2 square by 2 plus GZ2. Then it is P by rho 1 plus C1 square by 2 plus GZ1 plus P2 by rho 2 plus C2 square by 2 plus GZ2. So consider incompressible density is constant. So this is the Bernoulli's equation. For deriving the Bernoulli's equation from steady flow, consider these assumptions, you will get the final result. This is also very important. Next. These are the important applications of steady flow energy equation. First of all, we are going to take the nozzle and diffuser. What is a nozzle? Nozzle, it is a device which is used for increasing the pressure energy at the expense of, it is used for increasing the kinetic energy at the expense of pressure energy. Nozzle is used for increasing the kinetic energy at the expense of pressure energy, and diffuser is used for increasing the pressure energy at the expense of kinetic energy. I mean to say that in nozzle kinetic energy is more, in diffuser pressure energy is more. So this is the simple nozzle, and this is the steady flow energy equation. First of all, keep in mind few important facts. In nozzle is generally insulated, so Q is 0, and there is no work involved in nozzle, so W is 0. It is on the same height, so you can cancel out the potential energy. Then the equation become H1 plus C1 square by 2 is equal to H2 plus C2 square by 2. This is the equation. H1 plus C1 square by 2 is equal to H2 plus C2 square by 2. This is the equation. Initial kinetic energy is very less than the final kinetic energy. So C1 is very less than C2. So the equation becomes H1 is equal to H2 plus C2 square by 2. This is the equation. Right. So this is the equation for nozzle. In numerical problems, if there is heat transfer, then please don't cancel out. In numerical problem for nozzle, if there is work transfer, then please don't cancel out. This is the generalized equation for the nozzle. Right. Keep this mind, H1 is equal to H2 plus C2 square by 2. Next comes the turbine and compressor. See, in Rankine cycle, in Brayton cycle, we generally use work done by the turbine as H1 minus H2, and work done on compressor is equal to H2 minus H1. So these are the important terms. Steady flow, that means you are going to use this equation. Perfectly insulated, Q is 0. Neglect kinetic energy and potential energy. These are the important assumptions. Neglecting kinetic energy, neglecting potential energy. So the work done by the turbine is equal to what? It is equal to H1 minus H2, and work done on the compressor is vice versa, which is H2 minus H1. So we are using this equation directly in numerical problems. At that time, don't think from where these H2 minus H1 and H1 minus H2 came. It is from steady flow energy equation, taking into account these assumptions. We are taking into account these assumptions, and we are solving these equations, and we are getting these results. Please go through them. Next is the throttling valve. This is a very important. What is the throttling process? In which there is no heat transfer. First of all, keep in mind, in throttling process there is no heat transfer, there is no work transfer. It is an irreversible process. Throttling process is an irreversible process, and the enthalpy is always constant. It is the same enthalpy or isenthalpic process. So the equation comes out to be H1 plus C1 square by 2 plus GZ1 plus Q is equal to H2 plus C2 square by 2 plus GZ2 plus W. No heat involved. Q and W cancel out, potential energy cancel out. This is the equation. H1 plus C1 square by 2 is equal to H2 plus C2 square by 2. Same enthalpy, H1 is equal to H1, that H1 is equal to H2, that is C1 is equal to C2. So what are the examples of throttling valve? See, throttling, the restricted kind of flow. A practical example I am telling you, if sometimes you have opened the tap of a basin, right, whenever you open the tap, sometimes water comes out in the restricted manner, right, it does not comes out very freely. That kind of flow is a throttling process, right. Flow through a partially opened valve, is a throttling process. Flow through a very small opening, is a throttling process. Flow through a porous plug, it is also a throttling process. So please go through these important applications. We are going to solve the numericals next. So it is very important that you just go through these lessons very nicely. If you have any doubt, you can ask me in the comment section. Thanks a lot from my side. This is Harshit Agarwal.